In this presentation, we're going to use Excel to perform a simple nuclear decay simulation. We will imagine having a set of radioisotopes. Each individual radioisotope in a given unit of time has a probability of decaying and becoming something else. And so then as we watch the collection of radioisotopes, they will undergo an exponential decay. We will set up a spreadsheet rather like the one we had for the random walk simulation. So we will have our statistics in columns A and B. A will just be counting the number of steps, and B, which we've labeled the sum, will be the sum of the isotopes that remain the original original radioactive material. We have in the first row a single parameter, the probability of decay, which is sitting up there in cell D1. It's important that you include that cell not have a 0 in it. And then across the top, we are having each sample start with a 1. So a 1 will represent that we have the original isotope, and then we're going to use a 0 to indicate that it is decayed and become something else. So we want to start with all 1s to start with, and we're going to have 100 samples. So we're imagining that we had 100 isotopes to start. Again, in our simulation, a 1 will represent that the atom has not undergone nuclear decay, and a 0 will represent that it has undergone nuclear decay. And then with each step, an atom that has not undergone decay, that is still a 1, has a probability of undergoing decay, becoming a 0. And that probability is given by the contents of cell D1, which in the previous example was 0.01. And this probability will be a parameter in our simulation. So we will run the simulation for a given value of this parameter, and then we may study eventually the effect of changing this parameter. But for a given simulation, the parameter will have one value. So in our setup, we have a set of 1s in row 3. These represent the original 100 isotopes, and they are starting in column D. So then we have in D4, we are entering the formula equals D3 times the if function in Excel. And then the if function has 3 arguments, and the first one is rand, open close parenthesis, less than $D, $1, comma 0, comma 1. Okay. So we are multiplying D3, which was in this case a 1, and we are multiplying it by an if. So an if is going to test the condition. So rand is the computer's generating a random number between 0 and 1. And when we generate that number, we are asking if it's less than what's in $D, $1. That 0.01 that we have showing there for now, the probability parameter. So if the random number between 0 and 1 is less than the probability of decay, we're going to multiply by a 0, and multiplying by 0 will give us a 0, and hence that will be our representation of a decay. And if that's not true, then we will multiply by 1, and thus get 1 times 1 will be 1, and we will still have the parameter. Now we'll copy this formula down. At some point along the way, the isotope may decay, and then the value that we're multiplying by originally before the if is a 0. So once it's become a 0, it will stay a 0. Once it's decayed, it remains decayed. But while it's not decayed, it has a probability based on the if function of decaying. This is the nature of radioactive decay. And with our use of if, we've set this formula up so then it is the correct formula for all the cells, all the samples, and all the time steps. And so we copy the formula down, and then we copy the formula across. Now we return to the top of the spreadsheet to perform the statistics on our simulation. So we go to column B for the sum, and we enter a formula that sums over all the samples. So our first sum in B3 is the sum of D3 colon CY3, and this is giving us 100. So we started off with 100 isotopes with none of them decayed. And then we're going to copy down the sum formula down through column B. And so we've copied the formula down column B, and we see what we are expecting in our simulation, that the number of isotopes, that this sum represents the number of isotopes that have not decayed, that it is always decreasing. And once something's decayed, it stays decayed, and then more continue to decay as time goes on. Here we show an XY scatter graph of the sum, the number of surviving isotopes, versus the number of steps, and we see this decrease, this decay. With the graph highlighted, we choose quick layout number 9. We're going to right-click on the fit line and choose it to be an exponential. We are going to label the axes and give it a title. It's important that we do not edit the displayed equation. The reason for not resizing or otherwise editing the displayed equation is because we want to change the parameter in D1. Note here that we've changed it to 0.02, and this will update the data and update the fit formula if we did not edit it. But if we do edit that displayed formula, we are not going to see the updates we want to see when we edit the parameter. So we must hold off on editing this displayed equation until the end. One of the main characteristics of exponential decay, and therefore also of radioactive isotopes, is their half-life. So we start with a certain amount of material, and the half-life is the amount of time that goes by before we end up with half as much material. And this time is consistent. So if we start with some original amount of material and wait a half-life, we have 50% as much material as we started. If we were to wait another half-life, we would get 25%, or half of half, and it would continue on like that. Each half-life going by, we would get half of what we had before that particular half-life. In the case of our simulation, we're not going to be measuring in time, but in number of steps of the simulation. So in Excel, we did the simulation, and then from that we created an XY scatter graph, and we fit that to an exponential. I want to show you how to get to the parameters that Excel provided and relate that to this idea of half-life. So I'm going to go through a derivation and then just end up with a result. So if you don't follow the derivation, then all you really have to do is sort of use the result that I will have in 3 slides and put in sort of bright red. Okay. So Excel gave us this formula, y equals 95.036 times the exponential minus 0.018x. And the half-life is going to be related to that parameter which is inside the exponential. It's going to be related to the 0.018 in a way we'll show. So by definition, half-life is when you get half of the original material. Well, the other parameter, the parameter out front, the 95, is how much you start with, how much you have when x equals 0. So what we want to do is find the x, the time, where, and call it the half-life, where the amount is half of what we started with. So I want y to be half of what we started with, and then that is, I will call the x at which that happens, the half-life. So for y, I stick in half of what we started with, 95.036 divided by 2. That's y equals 95.036 times the exponential of minus 0.018. And now, instead of a generic x, I'm putting in specifically the half-life x. Next, we divide both sides by 95.036 since it appears on both sides. And so on the left-hand side, we have 1/2, and on the right-hand side, we have exponential of minus 0.018x half-life. Okay, to get rid of the exponential, we take the natural log of both sides, because the natural log is the inverse of the exponential. So taking the natural log of both sides, I get that the natural log of 1/2, that's the left-hand side, is equal to the natural log of the exponential of minus 0.18 x half-life. And log of 1/2 is just a number, and it happens to be minus 0.69315. So here I'm just showing you how I got that number, minus 0.69315, using Excel. So I just entered the formula equal natural log of 0.5. Okay, so again, we had that the natural log of 1/2 was the natural log of the exponential of minus 0.18 x half-life. We said that the natural log of 1/2 was minus 0.69315, and we also said for the right-hand side that the natural log and the exponential were inverses. So they undo each other, and we're just left with the inner argument of minus 0.18 x half-life. Okay, so there's a minus sign on both sides. We'll get rid of that. We're going to solve for x half-life. It's going to be that number 0.69315, and then it's going to be divided by that number that was in the parameter from the Excel fit. So this is the end result, that if you didn't follow the derivation, this is what you need to know. That 0.018 number came from the fit in Excel, and the 0.69315 is a constant related to the natural log of 1/2. Now what we'd like to do with our simulation is to vary that probability parameter that we had in cell D1 and extract the half-life for each of these different p's. So again, you change the p, you get a fit in Excel, you extract that number from the fit, and then from that number you can extract the half-life. And we want to see how the half-life depends on this p. So we'd like to look at how the half-life depends on p and make a plot of half-life versus p. So p was the parameter that we had in cell D1, so we are going to vary it. Then when we vary that parameter, we should see that the exponential fit, the data in the Excel spreadsheet and the fit of the data in the spreadsheet should update, and we will see new parameters in the exponential fit, and we're interested in the parameter inside the exponential. From that, we can calculate the half-life, and then we can make a trend line of this data. So here I'm showing my results when I varied the parameter p and extracted the half-life from it. So again, p was my parameter, which was in cell D1 in the nuclear decay simulation. When I varied p, my data and the exponential fit to that data updated. I'm extracting the parameter b from inside the exponential. I'm not worrying about its sign, I'm making it positive. And then I divided that number into, so it's the denominator, 0.69315 over that number, and that gave me the half-life. And then finally I made a plot of half-life versus p and got the graph that you see there. Now again, you're not going to get the same numbers because we're doing a simulation and your random numbers will be different from mine. In fact, it's possible, especially with the higher p-values, say the 0.07 and the 0.08, that if all of your radioisotopes decay, you're not going to be able to fit to an exponential at all. So if you are missing one or two of these numbers at the end, that's acceptable. That can happen. So vary the p, find the half-lives, make the plot of half-life versus p, and then play around in Excel and try to find the function that fits best to this dependence, and ask the usual questions. Was this a good fit? How do you know? Etc.